All right, conditional probability. Conditional probability is the probability of an event happening given that another event has already happened. Okay? So your friend rolls a die. He peeks at it, but doesn't show you. However, he tells you it's odd. Okay? So you already know that instead of there being a possibility of 6 numbers, there's only a possibility of 3 numbers. Okay? So what's the probability that it is a 5? That's a 1 out of 3 instead of 1 out of 6, because you already know it's either 1, 3, or 5. There's no chance it's an even because you were told by your friend. So given that it's odd, which limits the possibilities, it's 1 out of 3. If a card is drawn from a deck, what's the probability it's a heart, given that the card is known to be a 10? All right. Well, if you know it's a 10, you know there are 4 10s in the deck. And there's only one suit of hearts. So that's 1 out of 4, not 1 out of 12. So you're not looking at the 12 hearts, or 13, sorry. You're not looking at the 13 hearts. You're taking the 4 10s because you know it's already a 10, and then there's only 4 of those: a heart, a spade, a diamond, and a club. If a card is drawn from deck, what's the probability it's a face card given that it's black? Well, there are 26 black cards. There are 6 face cards. So, therefore, you know it's out of 26 cards. Okay? And there's only 6 face cards that are black. There's 6 that are black, there are 6 that are red. So it's 6 out of 26, which reduces, you gotta reduce when you can, to 3 out of 13. All right, if 2 cards are drawn from a deck without replacement, okay, that means you take a card out, leave it out, take another card out. Was probably the first is a jack and the second is a 7. Okay, well, the probability of getting a jack, there are 4 jacks and there are 52 cards. But if you don't replace it, now there are only 51 cards in the deck. The second being a 7, that's still 4 because the jack did not affect the 7s, but the jack did affect how many cards are in the deck. So that ends up being, if you reduce it, 4 out of 663, or 0.006 if you don't convert it to a fraction. If 2 cards drawn from the deck without replacement, again, what's probably the first is a 3 and the second is another 3. Now this is different. So there's 4 3s and there's 52 cards. Now the second pull, there's only 51 cards, but since we're looking for a second 3, there's only 3 of them left because you already pulled one out. That ends up being 0.0045, or if you convert it, 1 out of 221. Now, I'll tell you, that 0.0045 is rounded, so if you actually took the decimal that you got in the calculator and did that, it'd be 9 over 2,000. Okay, so this is this one. I'm sorry, my bad. The 0.0045 is that one. If you went with what it was in the calculator, that's the more accurate one, but it doesn't matter. I would accept either one. All right, a study suggests that 11% of teens with a tattoo, while 45% of teens have a piercing and 3% have both. So we're going back to our Venn diagram. All right, we have 100% here. We know 3% is in the middle. All right, if 11, we're going to put tattoos over here and piercings over here. So if it's 11% have a tattoo, 11 minus 3 is 8. 45 have a piercing, so 45 minus 3 is 42. If you add all those up and subtract, it leaves 47 that have neither. Okay, because these add up to 53, right? So what's the probability that a teen has neither? That's 47%. Teen has only one tattoo. Has only a tattoo. That's the 8. A teen has a tattoo given that they have a piercing. So if they have a piercing, there's 45 people with a piercing, 45% with a piercing. And to have a tattoo is at 3. And D and C are the same one, just worded differently. A teen with a piercing also has a tattoo. And a teen with a tattoo, so that's this 11%, also has a piercing. That's at 3. So 3 out of 11. All right. All right. Below are the results of the last test of the 14 males and 16 females. Okay. So we know that this is 14 and this is 16. And then I'm just totaling these up. This is 12 and this is 18. And either way, that ends up being a total of 30. Okay. We know 8 guys cheated. So this is cheating here. And this is not cheating. Okay. So, using the chart, what's probably the randomly chosen student is male? Well, there's 30 students total, and there's 14 males total. So that's 14 out of 30, which if you reduce that by 2, that's 7 out of 15. What's probably they are a cheater? Well, how many cheaters are there? There's 12 cheaters out of 30. Okay. This one we can reduce by 3. Actually, no, we do reduce by 6 and get 2 out of 5. An honest female. So first off, we look at female, which is 16. Didn't cheat. That's this number right here, 12 out of 16. And if we reduce that by 4, that's 3 out of 4. A cheater, given that they were a male. So given that they were a male means 14 on the bottom. And a cheater is 8. Again, both even. So we can reduce by 2 and get 4 out of 7. And a female, given they were a cheater. So how many cheaters were there? There were 12. So that's our denominator. And there were 4 females that cheated. So that's 1 out of 3. Okay, cannot get this to go down. Hold on. And last one. PE teacher is going to randomly pick teams for kickball. There are 10 seniors and 8 juniors in the class. If the first person he chooses is a senior, okay, so that's a total of 18, what's the probability the next one will be a senior? All right, so if there's 18 kids, one's already been picked, that leaves 17 on the bottom. Okay, what's the probability to be a senior? Well, if he chooses a senior first, there's only 9 seniors left. What's probably the second one will be a junior? Well, again, there's only 17 left. He picked a senior first. That means there's still 8 juniors. And since 17 is a prime number, those will not reduce, and we are done.